Hello everybody, and welcome to exercise 4 on page 149 of the workbook. And in this example, we are going to derive a special case of Gauss's law from physics. Gauss's law has to do with what happens if you integrate a vector field, an electric field over a closed surface. Okay, so let's read this together, get a feel for the setup here. So they start us off with something called Coulomb's law, and tells us what an electric field of a point charge located at the origin is going to look like. Here's our formula for the electric field. Notice that it's got an R in it, and so this field has radial symmetry away from the origin. Okay, now one thing, they give us a constant called epsilon in this problem, and I'm actually going to make a little change to the notation here. That's not a particularly good choice of notation because physicists tend to use that differently, so I'm going to just relabel that and call that constant K instead of epsilon and just try to be consistent with that alteration through the problem here. Okay, so let's continue here. And here's the key fact that we're going to kind of use throughout the problem. It can be shown that this vector field is divergence free. The divergence of E is 0 provided that we stay away from the origin. Because right at the origin, R would be 0, and we'd get a 0 denominator, so our field is not defined there. Okay, and so let's take a look then at part A here and see get a feel for what they're asking us to do. So they're describing two surfaces to us. Okay, so S1, that's the first one. This is an arbitrary surface that totally encloses the origin. Okay, so if we just start a picture over here, I'm going to put the origin at the center, and think of S1 as just kind of a blob. It has to be a closed surface. Okay, so it could look really wild. It could be bumpy. Think of it as maybe like the surface of a lump of clay or something like that. Okay, S2 on the other hand is a very regular surface. It's the surface of a sphere of radius A that also encloses the origin. Okay, so S2, do my best to draw a sphere here. It looks like that, and they tell us that its radius is A. Okay, so we'll label those two. Okay, and they'd like us to use the divergence theorem to explain why the integral, the flux integral over those two surfaces is the same. If you think about it, that's kind of surprising because these two surfaces look really different. S1 could be really irregular and bumpy, and S2 is a perfect sphere. And yet, we're being asked to show that the flux integral over both of those are equal. Okay? Well, how can we do that? Well, it turns out the key is to start by thinking about the region that's inside these two surfaces. I'm going to give that a name. W is going to be the solid region between S1 and S2. Okay, so in our picture, W would be sitting in here. Okay, and remember, you're seeing like a two-dimensional slice of this. Really, S1 and S2 are blobs. Okay, and W is like sort of a lump of clay with a little hole in the center of it, with that S2. Okay, and once we've chosen that solid region, let's give a name to the surface of the solid region. I'm going to call it S, and give it the outward orientation. Okay, now S is kind of an interesting surface because if you think about it, if W is this three-dimensional region in here, let's go ahead and just shade it so that we can kind of get used to thinking about that as being something that's solid. The surface of W actually has two parts. There's the outside surface, which is S1, and there's kind of the inside surface, which is S2. So what would an outward orientation mean? Well, it would mean, for example, that if you're at a point inside of W somewhere, escaping to the outside through S would mean that we have to go in this direction, away from the origin, so our normal vectors would point towards the outside everywhere. Okay, I'm doing my best to make them normal to the surface everywhere. So that's part of this outward orientation that we've chosen. But if we want to escape from W through the surface S2 and get to the outside, we actually have to go to this direction. That's the way that you get outside of W through the surface S2, so they have to point towards the origin. Okay, and that's a perfect sphere, so those normal vectors are a lot more regular than the other ones. Okay, so the red vectors that we just drew, they describe the orientation of the entire surface of W, both parts of it. Okay, and now we kind of come to the key observation here. What about the divergence of our electric field? Okay, our electric field is defined everywhere except at the origin. There's where we got the zero denominator. So if we just talk about this solid region W, W doesn't contain the origin. It's the part of our drawing that's between S1 and S2. So that means that by this fact that they gave us up here, the divergence of E is equal to 0 everywhere inside of this solid region W. Okay, we're going to use that fact, and it's going to lead us exactly where we want to go here. All right, so by the divergence theorem then, here's what we can say. So the integral over S, okay, and remember S is this two-part surface of W, that has to be equal to the triple integral over W of the divergence of E dV. That's exactly what the divergence theorem says. We can take this flux integral on the left and replace it by a triple integral. But we just made the comment above that everywhere in W the divergence is 0. So this integral that we're doing, we're just integrating the 0 function over dV. That's going to give us 0. Okay, I'm going to label that equation 1. So we've just proven that if you integrate the electric field over the entire surface S, which has these two parts, you're going to get 0. Okay, but then we remember that S is comprised of two different pieces, the S1 and S2. Okay, so we get another fact out of that. Okay, where is that going to lead us? Okay, well, that's going to tell us that the flux integral of E over all of S can be broken into two parts. Okay, the flux integral over one part of the surface, the S1, plus the flux through S2. Okay, there's only one problem, though. This equation is not quite right the way that I wrote it down. Okay, let's take a glance back at the orientations. Okay, how were S1 and S2 oriented at the beginning of the problem? They're both oriented away from the origin. So take a look back at the picture that we drew up here. Okay, do the normal vectors that I drew on S2 agree with an orientation away from the origin? They don't. They go toward the origin in exactly the opposite direction, okay, that the problem said. So to compensate for that discrepancy, what we have to do is to go down here and say, oh, the sign of this integral is not right. It's got to be negative to compensate for that difference. Okay, and I'm going to make a note here where that came from. This is negative because S2 is oriented away from the origin. All right, so let's put it all together. What does all of that tell us? Well, if you look back up at equation 1 here, this integral is equal to 0. That's what equation 1 said. So we take equation 2 and just put a 0 on the left-hand side. Here's what we get. And since we've got a 0 on the left-hand side, kind of natural just to add the flux integral over S2 to both sides of this equation, and look what happens. We get exactly what we wanted to show here. So on the left is the integral over S2 of E dot dA, and that's equal to the integral over S1 of dot dA. Okay, so as amazing as it seems, that's telling us that even though S1 and S2 are really different surfaces, one is kind of a irregular blob and the other is a perfect sphere, we're going to get exactly the same value for those two integrals. Okay, and in the next video, we will use that observation to see if we can come up with a special case of Gauss's law.